So
Yep.
kia ora koutou katoa, ko George Tukuunga. So thanks for the introduction, Josh, and thanks everyone for coming along today. So as you might expect, my name is George. I'm a mechanical engineer from the Department of Mechanical Engineering at UC, and I've recently completed my PhD, which is all around understanding the strength of people with C5 to C7 tetraplegia in a bit of an engineering context, I suppose. So originally when I was starting my PhD, or what drew me into it, was I've always been interested in design engineering, and this topic kind of came up, I suppose, and I was taken by the idea of doing work that would hopefully be able to have a positive impact on people's lives. And so the whole basic idea around this research is, if you want to be designing things for people with reduced function from an engineering point of view, that you first kind of have to understand their baseline strength and areas of strength. So that's what I'll be talking today about. So there we go. So in the overview, I'll talk through basically a bit of a PhD intro before going into a little bit more detail about the strength study that was done, the work that was done on a fitted model and a biomechanical model. And then I'll talk a little bit around the future research plans that could be done for this work before opening the floor for questions. Cool. So in terms of the PhD study, so by looking at the research, we know that annually there's around 10,400 new cases of people getting tetraplegia in the US alone. So a lot of people having this kind of injury. The statistics show that these are dominated by males and also dominated by traumatic causes, which means that we're left with a population of people that have had their life kind of rapidly changed. So of these people, the most common injury levels were C5 to C7, and then this slide here basically is just showing what muscles they have, which I'm sure you're all aware of. So obviously the biceps and having no active elbow extension being the main limitation of people with C5. C6, similar, still no active triceps, but the addition of the wrist extensors, and then C7, slightly more function, mainly being that they're able to use their arm above their head, which is something that we'll be looking into when I talk about the modeling part of my research. Cool. And so what are we trying to do, or what did I try and achieve with my PhD? So the main idea was to improve the information that we know around the strength of people with C5 to C7 tetraplegia in a bit of an engineering context, and that's useful would be, this information would be useful for designers, medical professionals, and people living with tetraplegia. So to start with, the idea was that we would do some physical testing with the strength study, and then that we would develop some kind of statistical or mathematical model to try and make that data a bit more usable. And then parallel to that, we would develop a theoretical model or a biomechanical model, and then be able to make comparisons between those two things. Cool. So starting off with the strength study. So previous work that has been done using isometric strength tests, so strength tests where the person doesn't move, have only evaluated a single direction. So if they were measuring a range of points, they would only be looking at, say, push strength, pushing just horizontally forward. 4 studies that did look at multi-directional force, so forces obviously in a number of directions, whether that's in a single plane or in all directions, they only looked at a limited number of postulates. So this really meant that there was an opportunity for this research where we'd want to have a look at a number of points within the range of motion, but also try and capture data that's not just in a single direction. So looking at multi-directional force over a person's range of motion. And so this was kind of the focus of the study to help improve the understanding of the strength capabilities using quantitative testing. So this photo here shows a side picture of the strength testing rig that we developed. So this was designed and developed at UC. So we have basically just a platform that enables a wheelchair to be attached to the bottom of the platform. There's two handles. Each of these handles have a load cell that enables us to measure force in all directions. And these handles are adjustable in all directions. So we can move them in the superior or the inferior position, or forward and back. And the test rig has also been designed so that we can change the width of it. So if we wanted to look at not just a single plane in future studies, that would be an option that's available. And we also made it so that if we wanted to change the handle in future studies, that the handle has a cup, so you could actually change that adjustment. But by putting that all together, it gives us a range for an area of 1.3 by 1.5 meters in the sagittal plane, where we can test a total of 224 discrete test points. So each of these test points are 100 mils apart, but obviously there's going to be some test points that are never going to be reachable. Cool. So this picture here just shows a bit more of a close-up on our testing handle. So when we were doing tests with people, having people with tetraplegia in, one of the things that we did was make them use a grip assist. So, and basically that was because we wanted to try and make sure that the data that we were gathering was reliable, and that grip strength wasn't a limiting factor. So we were basically eliminating that, which is something that needs to be considered when this data is used. And then so for each test point that was completed, so we would pick a test point in this range of points, and we would get the person to push forward and then radially around for 1 1/4 turns. So the way that I've normally described this is it's like you're turning a handle, except the handle doesn't move. So you're changing the direction of the force that you're pushing without the handle moving. So at the start of the test, we'll normally get the person to do a few practice to get familiar with it before starting doing any testing. And then the reason that we get them to do 1 1/4 turns is just so that we get some overlap in the polar plot or the test data that we see. So this next slide here shows an example of a test plot. And so this shows us the direction that the person was pushing. So 0 degrees being pushing horizontally forward in the X direction. So they'd go forward and then down and around for 1 1/4 turns. And this basically just enables us to see whether there's good overlap or whether we're getting consistent data all the way around the test point. Cool. Don't think I've missed anything, so I'll keep going. So some initial results. Basically, how does the testing work? That's something I should probably mention. So the method that we would use is we'd start with a central test point. This would basically be used for retesting to check for fatigue. And then we would go down a chosen column in 200 millimeter increments. So they would get them to do a test if they could reach it. And then they would get a minute rest time. In that time, we'd be moving to the next test point, which was in another 200 mil. So basically, we are able to capture data over a course grid over the person's range of motion. And so when we do that, we get something that looks like this. So this is some initial results that were from a able-bodied or a non-disabled participant. And we can see that generally they are able to push a good amount of force or a reasonable amount of force or consistently in all directions. So we see more kind of circular or full elliptical shapes. This is another person, non-disabled. And again, we see a similar kind of trend, but this person had less force in directions tangent to the maximum force. We can see on the plot that there's just been a rough stick figure of a participant, just to give you an idea of where the person's shoulder is and a rough kind of position that they're in, but that was the same for all of the plots, so that's not something that is being adjusted for each of the people. And then here we have some initial results from someone with C6 tetraplegia. And so these initial results basically showed a pretty contrasting result where the polar plots that were gathered were really thin and elliptical. So we can see that in directions perpendicular to the maximum force, that the person wasn't really able to push very much or produce a large amount of force in that direction. When we were kind of analyzing this, we kind of saw that these the maximum forces tended to be going radially out from a position that was roughly somewhere in the middle of their wheelchair backrest. Cool. So I'll talk a bit about how we've analyzed these results, but this was, yeah, the first few results that were completed. One thing just to touch on was repeatability and fatigue. So I did say throughout the test that we would pick a test point and retest it to check whether fatigue was affecting the results. This plot on the left here shows 21 retested polar plots from one of the initial participants in the study. And this basically was just done to show or to determine whether the method is enabling valid and reliable results. So this was a big green tick, I suppose, of getting being happy that we could get a good amount of repeatable data. The main area of variation for this test point was in the 0 to 30 degree direction, and this was basically in the maximum force kind of direction. So this variation would be due to the person, the amount of effort the person was putting in. And so that's probably a good point to also consider with these results, is that they're not capturing absolute maximum force that the person is generating, but rather trying to get a representative strength. So from a design point of view, we're trying to get data that could be used and work out areas of high strength using this method. This plot here also shows the first 5 repeated polar plot tests for the first 3 participants. And again, it shows good repeatability and that fatigue wasn't affecting the results. So for each test, it would normally take around 1.5 hours, and would require a minimum of 5 retest points throughout the testing. So that enables us to basically make sure that we're getting data that's not getting affected by fatigue. So for the people with tetraplegia that were tested, we ended up having 10 participants of a range of injury levels from C5 to C7 or C4 to C7, and 2 different wheelchair types that were also noted. So basically to give an overview of the results and to be able to compare to previous studies, what we did was worked out a method to average what the maximum force we got for each of these different injury levels. And so to do this, it's probably easiest to go back to one of these polar plots. But for each of these test points, the maximum force value would be recorded, and then that value for all of the test points would be averaged. And so that would give us one value that we could then average for each of the test participants, so that we could see what the kind of overall trend was for the people that we had tested. And what we saw was what we, I suppose, expected, and it also agreed with previous test results that people with C7 had a larger average maximum force, and that people with the higher injury levels had a lower average maximum force. There were a few interesting comparisons that were made when looking at the test data. So this polar plot here has 2 participants' data who both have the same injury level, but you can see that there's quite a large difference in the shape of the polar plots. So you can see here that participant P08, their polar plots were a lot more full compared to participant P04, and that their range of motion, the amount of points that they were able to reach and where those points were, was also something that was had a large difference between participants. So one method that we used to kind of look at injury levels in a bit more detail was just to consider the shape of 3 different participants that all had the same shoulder point, and to look at detail at 4 test points within the participants' range of motion. And so this is shown here. So for those 4 points, these are the polar plots. I'm not sure if the contrast is making it very clear, but this, by doing this initial analysis, we saw that the higher injury levels, so C7, had full elliptical and larger elliptical shape, and that this shape was similar for people with C6, and then people with C5 had considerably smaller but more circular shaped polar plots. So the main reason that this was investigated was because we wanted to see or try and work out whether there were trends for injury levels, and there was a hypothesis that we had that people with different injury levels may have kind of characteristic strength profiles. So this was something that we were trying to investigate. And so initially, when we started the study, or when we looked at the results, the hypothesis was that people with higher injury levels would get increasingly thin polar plots. But this kind of started to show that that is not necessarily the case, that the radial force, we can see that the maximum force, or the radial force, did decrease, but that the force that's tangent to that, so we call that the minor axis, that actually decreased at a different amount. So to analyze these patterns, we worked out, we normalized our data by having a number that was the average minor axis divided by the major axis. So for each of the test points, we would capture the maximum force value, and then what the 2 force values were that were tangent to that, to get this number. And then all of those test points were averaged so that we could again get just a single number to compare and get kind of an overview to see whether there were any trends happening for different injury levels. And so this polar plot here, or this plot, sorry, shows the result of that. So our initial hypothesis was that that C7 would be somewhere similar to able-bodied people, and that we'd have a trend line going down like this, where the polar plot shape gets thinner and thinner. So a high minor axis to major axis ratio. So if that number was 1, that would mean that it's a perfect circle. So basically, this is a measure of how thin the polar plots are for each participant on average. And we kind of saw that there wasn't any clear trend just because of the number of people that we had tested, that we'd obviously need to have a bit more data to say with any kind of confidence. But loosely speaking, the people with the higher injury levels started to have more circular polar plots. So to take this one step further, what we did was just look at the force, the changes in force for different injury levels, just looking at what their maximum force was, and just looking at what their minor force was, or that direction that is perpendicular to their maximum force. And so this kind of revealed that the reason for the trend in the previous slide was because the maximum force was decreasing more rapidly than the minor axis force. Sorry. Yeah. And so basically, that was one of the main outcomes of our strength study. Yeah, and I think what we speculate the reason for that is that the forces, or the directions of force that are perpendicular to to the maximum force, that those forces are actually not necessarily limited by the arm strength of the individual, but by external factors such as they don't want to push themselves out of their wheelchair. So if they're pivoting at the hip because they have a lack of trunk stability, that is a limiting factor that would be common for all injury levels. And so this is why we think this number is kind of similar amongst different injury levels. So another comparison that was made was looking at the difference in the types of wheelchairs that we use. So here we can see two people with the same injury levels at C5, but they have different wheelchairs. So again, this was a contrasting result that was seen throughout. So there wasn't a clear trend from the small amount of data that we did in terms of range of motion or the kind of shape or the sizes of polar plots, specifically just looking at injury level. And so this is something that we would want to look into a bit detail in future work. And the main way to kind of test this, or the main thing that we want to find out, I suppose, is whether the shape of the polar plot is influenced by the wheelchair type, or whether it's the other way around, in that their strength defines what kind of wheelchair they need to get put in. And so one way that we'd want to test that would be by getting someone to use two different wheelchairs, or get the same person use two different wheelchairs, which was something that we tried to do in the study, but we weren't able to find anyone willing to do a second test using their alternative wheelchair. So in summary, in the strength study, we created and validated a test method as a way to rapidly gather multi-directional force data for participants in a seated position, and that this was a far more efficient method than the previous, which only looked at single isometric force directions. In total, we tested 21 participants, and we were able to kind of look at, or the results highlighted a number of differences in strength and raised a number of questions in terms of future work that can be done to look at the causes of these different strengths. The results of the average maximum force agreed with the trends that were in past studies, and the insights from the polar plots showed some interesting patterns in terms of the shape of polar plots for different injury levels. Cool, so that is the first part. Now I'll talk about the fitted model. Cool, so starting with the fitted model, the main question that was kind of asked was, is there a way to improve the usability of these experimental results? So the current polar plots, they show a large amount of data, a large amount of information in a single polar plot, or in a single plot, which is can be good, but it also can make it quite difficult to use. So if we wondered if there was a way to predict the areas of expected force in between the test points, and whether this was also done to try and work out whether it's possible to create characteristic maps for each injury level. There currently was no available of this kind available to designers. So by designing something like this, it's something that could actually be used by people like engineers to evaluate designs or strength requirements for things like prototypes if they were trying to develop them, and hopefully speed up the design process when they do that. So we can see here is an example again, the C6, person with C6 tetraplegia. What might you do if you wanted to work out how much force they could push straight up in this point here that is directly in the middle of 4 test points? Currently, you'd kind of just have to estimate it, but the fitted model wants to develop a way to do that. So to create the fitted model, we first had to filter the data from the strength study, and we did this by splitting it into 12 directions, so 30-degree increments, so that then we could make a single model for each direction of interest. To capture this data, we would use a tolerance or a range of plus or minus 5 degrees to capture the maximum force around each of those directions. And then for each of the participants, the data was normalized by dividing it by the maximum force for that direction. So this basically made it easy to compare the results between different participants, because we would know that a force value of 1 shows the maximum. So this enables us to look at where the areas of high strength are and not necessarily what those values are just in terms of force. And then the curve fitting tool within MATLAB was used to generate equations. And then there's this unreachable points discussion. So to start with, a model was made to try and capture the whole test area. So test points that were unreachable were included, but I'll talk about how that kind of impacted the initial results. So to choose what size model we used, I did a investigation of the average adjusted R² value, so looking at the accuracy of these models, and a fourth order polynomial was selected. So this was this had a good fit of the data without the need for 21 different coefficients, which was what you'd need for a fifth order model. And so this here is an initial plot of or initial example of one of these directional contour plots. And so we can see here that the unreachable points, which are in blue, which should be 0, were included to try and fit the data to. However, this meant that the model had a hard time capturing the areas of high strength. So we can see here in this this fitted model that it only really gets up to around 0.7 max strength, that we don't actually know the complete areas. We haven't captured these areas from the raw data where there is closer to the maximum strength. So that was something that was updated in a future polar plot. So refined polar plots were made. So 24 polar plots were made for each participant. So one polar plot was made using the raw data, and then one was made using this modeled data, just so that comparisons could be made, which resulted in a lot of contour plots being made. And then for each of these contour plots, there was a table of constants that would basically enable you to capture the data or to work out what the force would be without having to look at the polar plot if you so desired. And then that would mean that you could work out what the force would be for a certain direction and a certain position. And so using this updated method, the updated method was around this defining what test points were included in these directional contours. And so for the refined plots, test points that were not reachable were actually excluded. So this meant that when you were plotting it, you needed to know the range of motion and the reachable points that the participant was able to reach. So we'll see here that they had a lot better fit, but they don't have this kind of sea of blue area where the points were unreachable. But we can see that using this updated method for the point selection, that we get a much greater accuracy in terms of getting areas close to one, which actually show that this would be like the maximum. The area for this person, you would get the maximum force output. So here is an example of the table of constants that you would get for a specific direction. And if you knew the maximum force for this direction, you could use these numbers and the equation to then, for a given location, it would tell you what percentage of the maximum force they can push for that direction. Just quickly, there was also an investigation to see whether a general model could be made to reduce the number of test points that are needed during testing. And so this was done using non-disabled participants. So the test data from 6 non-disabled participants was combined and averaged to then get a model for non-disabled participants. And then this was used to compare to a person that hadn't been, or a person's data who hadn't been included in this model to see how similar the predictions would be. But the outcome of this was that it wasn't overly useful, and that more development would be needed to create a model that could be used to kind of make predictions and reduce the number of test points. But yeah, it would be something that'd be really useful if you could say halve the number of test points that you needed to do, and then use a generalized model to work out what the points would be in between. So in summary, the fitted model enabled a better use of the multi-directional strength data and enabled us to investigate whether there were patterns for certain directions. However, it basically showed that we needed to get more testing to actually be able to make a comment on whether there were patterns. But yeah, the model complements the results of the strength study and makes the data more usable for designers. And general areas of high strength can be determined using these models, which could be helpful. And then finally, as we kind of just talked about, there was a comparison between a fitted model more generally and the empirical results. However, more research or more development is needed to make a model that's going to be used for making force predictions. Cool. So that's that little section, and now we're on to part 3 of the biomechanical modeling. Cool. So starting with this slide here, basically it shows a bit of the motivation for what the biomechanical modeling was doing. So if we're looking at these polar plots, we see we got a side view of the person, and we also get, if we look at a single test point, different shapes with different injury levels. And so the main motivation for the biomechanical model was to see whether there's a way that we could recreate these polar plot shapes just by using some biomechanical analysis and doing some basic mathematical equations for a 2D scenario. So to set up a model, we defined this as our person, and we had the lengths and the mass of each of these segments defined using data that was found in the literature. Definitions were added to make sure that joint angles were acceptable and possible in real life. And then the location of the center of mass of each of these points was also determined so that we could use that when we're trying to work out what the limiting forces are for each direction. And so this is a pretty simplified model, but the whole idea was to first investigate whether it's possible to do modeling before then doing more work and looking at things like a 3-dimensional model or so this basically, this model, the main limitation or the main assumption is that the joints are kept in the sagittal plane or kept in line with the sagittal plane, so doesn't allow for any out of plane movements. And so for a given test point, so this here is an example of the kind of test environment. For a given test point, we would have limitations on what the joint torques are for each limb. So that's looking at elbow extension and flexion, shoulder flexion and extension, and pivoting at the hip. So we would evaluate these limits as our, I suppose, limiting force or our maximums for what would influence our polar plot. So we have our joint torques, we have tipping at the hip, tipping at the back of the top of the backrest, friction from sliding forward on your seat, and self weight. So the reason that some of these are a little bit unusual is just because we wanted to try and make sure that we're getting limits for all directions. So for example, the self weight limit, if you were to pull yourself up on the wheelchair, once you are off the wheelchair, then you're not going to be able to produce more force than your self weight. So that would limit that side of the polar plot. This slide here shows a little bit of how the limits for each articulation were calculated. So for a given test point, the joint angles would be calculated by the model. Then we used just a maximum value and we multiplied. So for example, if we were looking at shoulder extension, the maximum value would be this -79 newton-meters. Depending on what the shoulder extension was, then that would give us a percentage of the maximum that we would expect for that articulation. And then depending on the injury level, we also had these factors that we could use to basically, in a crude way, simulate a person with reduced strength. And so these values here were based on the muscles that are involved for these articulations. So here we can have a look at some of the example test results that were done for this here, which is test point 91. So this here shows what our polar plot would look like. So we have a number of different lines that show us the different limiting forces, and then this pink line shows us the smallest area or the smallest polar plot. So we would expect that this would be the limits of what people could push based on our model. And so looking at the results, it kind of shows a similar trend to what we had in our strength study, that being the non-disabled participants were able to produce more force perpendicular to their maximum force, so more circular polar plots, and that people with tetraplegia had polar plots that would get considerably smaller as the injury level got higher. And so we can see that the scale is also changing between C6 and C5 because the limiting forces are getting smaller for that test point. And the main reason for this was the lack of elbow extension. So that was often a limiting factor for these. The other most common one was pivoting at the hip. So because people who are non-disabled did have an amount of force that they could use to support themselves in the wheelchair and stop them from pivoting at the hip, this meant that this made their polar plot a lot larger compared to the participants, or simulating a participant with tetraplegia. So yeah, this initial model was just done keeping the same size person, masses, and joint lengths the same, just to have a look at the general trends. But yeah, because it's only a 2D simplification, that's a limitation of the model. And it's also got a pretty crude way of working out what the limiting torque would be, which is something that would want to be, both of these things are things that a future model would want to improve on. Cool, so yeah, so these initial results did again agree that there was a reduction in polar plot size with injury level, and it can be a useful tool to kind of work out what were the limiting factors for a certain test point. The reachable test points were one limitation of the model, as we've stated earlier, that it doesn't allow for any out of plane movement. So that kind of those simplifications limit what the model can be used for. Another thing that was done was a comparison of the model to actual results from the strength study. So we can see here that these are 4 comparisons that were made. And the reason that the shape of the body look a little bit strange is that the hip position and the shoulder position were actually matched, as these are kind of key positions from for the limiting forces. So to make sure that we got accurate results, those were matched. And so the red shows us our model polar plot, and the blue being the test data. But because it's quite small, I have got a zoomed in version looking at test point 91. So that was the same test point that was shown more previously. And when we compare it, we see that For a person with non-disabled, that the limiting force from our equations is quite a lot larger than the actual force that they produced, which is kind of expected. We would expect that, yeah, basically these pink lines, you wouldn't expect the limiting force to go above that. However, for our people with tetraplegia, there were a couple of times where the limiting force was larger than our modeled. And the reason that we've kind of put this down to is, again, some of the simplifications of the model. So when the model is simulating a person's strength, it's not allowing for any adjustment in their body position. And so that can actually influence the joint angles, which is then going to influence what the limiting torque would be predicted by our model. And it would also, by moving, it's going to change the center of mass locations, which will also have an influence on the limiting factors that are used by the model. But we see here that for the person with C6, it actually captured the point surprisingly well. And then here for our C5, again, we see that this green line, which represents elbow extension, that their force is a lot larger than what we thought would be limited. And so this may be due to the participant having some kind of trick in the way that they push forward without needing to use any elbow extension. So the model is not really able to allow or take into consideration these kind of tricks, I suppose. So these last few photos kind of just show some of the limitations of the model. So for example, for this test point here, the model assumes no out of plane movement of the elbow or of the upper arm, but in reality, that's the position that the participant used. And then here again, we see, as we kind of touched on, a change in posture for the same test point. So the participant moving their body as they do the test point to try and increase the strength that they can produce in different directions. So in conclusion, the work presented has contributed to the understanding of the upper body strength of people with tetraplegia. Overall, we've improved the methodology for measuring multi-directional isometric strength by looking at multi-directional strength in more detail. We have made some fitted models that can allow us to look at more detail of certain directions. And a basic biomechanical model has provided insights into some of the factors that will limit the size of the maximum force exertions. The development has shown that it's possible to simulate a reduction in strength, but we will have some improvements that we would want to make to that. So I'll talk about that in a couple of slides. Would just like to make sure that I don't forget my acknowledgements. So big thanks to all of these people. So Mechanical Engineering Department, my supervisors, Shane Gooch, Digby Simons, and Jennifer Dunn, and the workshop staff and the technical staff at UC, specifically, or in particular, Julia Phillips, who helped getting the strength measurement test rig operational. So future research plans. One of the things that we'd want to use this testing methodology for would be to try and understand the deltoid to tricep tendon transfer in more detail. So if we were able to get someone to do this testing before and then maybe a year after getting their tendon transfer, this would enable some pretty interesting insights into the effects of this elbow extension or this added functionality. And then there's a number of improvements that we'd want to do with them in terms of modeling the capabilities of people with physical impairment. So as the main limitations of the model were that it was 2D and simplified, I think if we did some testing and had captured joint angles, that this would enable a 3D model to be developed. So instead of doing a large number of test points, you could get a model working just for, say, a single test posture and really understand what's happening in 3D kind of context before then using that to try and make predictions in a 3D kind of sphere. Cool. So with there we go. Oh yeah. So the main activities that would be need to be completed is obviously further data collection. So some of the limitations of our strength study were mainly because we didn't have enough data to try and actually get comprehensive, to be confident enough of the kind of outcomes. And then, as I kind of touched on, improving the biomechanical model to incorporate 3D stuff